right? So let's talk about carbocation rearrangement, right? Rearrangements often occur when you have a reaction that proceeds through a carbocation intermediate, and a rearrangement happens if the new carbocation, if the new carbocation is more stable than the intermediate that you get from whatever the step preceded that to make it, right? So whatever step that happened before the carbocation, if that carbocation, if you can make a more stable carbocation through a rearrangement, then oftentimes you're going to see a rearrangement. Rearrangements can also accompany any of the aforementioned reactions that was shown on the previous slide: substitution, addition, or elimination. All of those can involve a rearrangement if they involve a carbocation intermediate that can be stabilized by rearrangement. And generally, your rearrangements are going to be either a hydride shift, and that's just a simple, like the last example that was shown on the previous slide, a migration of hydrogen and a pair of electrons, right, towards a positive charge, or a methyl shift, which is the migration of a methyl group and its electrons towards a positive charge, right? And these migrations happen again for stability. If you can go from a less stable carbocation to a more stable carbocation through a rearrangement, that rearrangement is going to happen. All right. So let's look at a reaction involving a hydride shift. Right. This is a simple reaction. We've already covered it. It's a secondary alcohol. I'm reacting it with HBr, and the arrows are here. Right. The oxygen is going to attack the hydrogen doing proton transfer. Then you break the HBr bond to get to this hydronium intermediate shown here. Right. Now the hydronium is is an excellent leaving group, and so I can show that leaving by breaking the carbon oxygen bond, and that is going to result in a carbocation that's shown down here, right? The carbocation is secondary. The carbon next to it is tertiary, right? So the idea is that I could potentially put the positive charge on a tertiary carbon and take it off the secondary carbon, make it more stable, right? How could I do that? Well, I have the hydrogen highlighted in blue. I could take that hydrogen and the pair of electrons that are in the carbon hydrogen bond and move the whole atom and the electrons towards that carbocation, and I'm going to make a CH bond right there where the carbocation is. And by the same token, the bond that I broke, the CH bond that I broke, I'll put the carbocation on that tertiary carbon, and you can see that here. Right, so the hydrogen and the electrons migrated to the positive charge. That put the positive charge on a different atom. That atom is tertiary, and because it's tertiary, it's a more stable carbocation than the secondary one that I formed when water left as the leaving group. Final step is just to now react that with bromine, right? And I have that arrow showing that, and this is my product, right? But the intermediate carbocation is what we dealt with, and that hydrogen shifting over, right, caused that carbocation to go from secondary to tertiary, and in turn it made it more stable. All right, so let's look at another reaction. Now we're going to look at a methyl shift. All right, same reaction. So I'm going to react this. Oxygen is going to attack that hydrogen, do a proton transfer, lose bromine. Here's my hydronium intermediate. Right, I'm going to take that, lose water as my leaving group. Again, I have a secondary carbocation. Notice I have that methyl, that CH3 highlighted now in green, because that atom and the electrons are going to migrate to where that positive charge is. Right? And I'll put the arrow in here. The bond and the atom, the electrons in the bond and the atom shift over. So now you're going to have a bond where that carbocation is between that and the methyl group. And because you broke the carbon-carbon bond where the methyl group is, the positive charge will now be on that carbon. So let's look at the intermediate. This is it, right? I broke the carbon-carbon bond. The methyl group shifted over. Now the positive charge is on the other carbon, because how do we form carbocations? We take electrons away from carbon, right? So now I got a tertiary carbocation as opposed to a secondary carbocation. The tertiary is more stable, which is a good thing. I just need now to react that with bromine. You can see the arrow there, right? And now that's my product, right? So I really did all of the information we talked about led us to the point of talking about hydride shifts and methyl shifts as rearrangements to form more stable carbocation. So let's conclude here, right? So what is a carbocation? It is a positively charged carbon. Carbocations are formed when you take electrons away from carbon. Carbocations are stabilized by hyperconjugation. They can also be stabilized by resonance or just by simply reacting them with a nucleophile. Carbocations can rearrange to go from less stable to more stable. Methyl shifts occur when a methyl group and its electrons migrate towards a carbocation. And then hydride shifts occur when a hydrogen and its electrons migrate towards a carbocation. So I hope you got something out of this video. I'm going to stop here. If you have any questions, you can always shoot me an email. I'll leave my email address at the end. And study hard.